Now, the day is, let's have some definitions of the day. If I said to you, I want you to go outside and get a clock, so you've got a clock, all right, I want you to go outside, start your clock, and then stop it one day later. How would you do it? You've got no other modern equivalent, no electronic aids or anything like that. What would you do?
You wait for the sun to come back in the same spot.
Right, where would be a good spot to start and stop from?
Sunrise.
Sunrise you might do. So you might go from just when the sun is just peeping over the horizon. You might go from sunrise to the next sunrise. Okay. Which would be best? Some people said noon to noon. You could do noon, which is when the sun reaches its highest point. You could do from one noon to the next noon. Or I suppose you could do sunset to sunset, couldn't you? I don't know what sunset looks like, really. Which of those three would be the better one to do, the best one to do? But they will be the same. Why do you like noon?
Because you have to measure, like, start sunrise or sunset absolutely.
It would be, wouldn't it? Because the sun is so bright and it makes the sky around it change colour, doesn't it? So to actually look for the disk of the sun, when does the disk of the sun just touch the horizon? That's going to be quite tricky, actually, isn't it? Yeah? In theory, if you could do them accurately, they'd all give the same time, wouldn't they? They would all take one day. Yeah? However, this one would be the better one. Those of you doing shadow stick project, tell us about how you might actually do that. Yeah? You could put a stick in the ground, couldn't you? Have you seen this on the controlled assessment thing? You could put a stick in the ground, measure the shadow, and when the shadow comes to shortest position, that means the sun's at its highest position, and that's what we call local noon. All right? So these are a bit tricky to measure, so let's stick with noon to noon. In theory, noon to noon takes a day, okay? And it does in fact take 24 hours, okay? What's another definition of the day? What's another way we could measure the day? Yeah, you could zoom out, couldn't you? You could actually zoom out in computer games, take what's called the God's eye view, and if the Earth is spinning, then you could say how long does it take the Earth to do a 360-degree circle, okay? Think of the Earth like a spinning football and literally just how long it takes to do 360. Now, the rather strange thing is that doesn't take 24 hours, that takes 23 hours and 56 minutes and 4 seconds. Well, you don't use over 4 seconds. Yeah? This doesn't take 24 hours. The Earth does not rotate once every 24 hours. It rotates once every 23 hours and 56 minutes. Okay? So, the important thing is, there's a difference here of 4 minutes. Alright? There's a 4-minute difference between sunrise to sunrise. If you prefer to think of it like that, that's absolutely fine. It would be difficult to measure, but you have absolutely got the right idea. Alright? The sun at any point, the sun just over the top of the music block. Alright? Sun just over the music block, as long as it's the same point every day, would take 24 hours. Okay? If you could, and we can't very easily, but if you could zoom out and look at the Earth going round, you would get this 23 hours 56 minutes. Okay? Now let's clear up a couple of mysteries. How on earth can that be exactly 24? Surely that's a miracle, isn't it? How is it that the Earth, the sun in the sky, takes exactly 24 hours to the nearest billionth of a squilly second? 24 hours. Exactly. How does that happen? Is that, what's going on?
We made it that way.
We did, didn't we? What's the definition of an hour then? Yeah, it's basically a day divided by 24, isn't it? All right? So why is the day exactly 24 hours? There's no mystery to it. It's because we took the day, the sunrise to sunrise time, and sliced it up into, well, I think the ancient Egyptians, 2 lots of 12. There were the 12 hours of the day and 12 hours of the night. Whoever invented it, the system that's come down to us still has the day chopped up into 24 equal slices. So don't be looking at that number and thinking, gosh, isn't that amazing? Not at all. We define the hour to be a 24th of exactly the time it takes for the sun to return to the same place in the sky. Okay? This type of day, let's give them different names because they are different, in your spec is referred to as a solar day. All right. I think in the handout it calls it a synodic day, which is the correct term, but I think that's the word you need to know. That's called a solar day. Clue. Sun. Yeah. The first suggestion, the position for the time for the sun to return to one place, same place in the sky, is 24 hours. Okay, because we define the hour to be a 24th of that. All right. The mystery one is this one. That isn't the time it takes the Earth to spin. The Earth to do a 360 spin does not take 24 hours. It takes 23 hours and 56 minutes. Okay. This has a rather grand name. It is called the Sidereal Day. All right. Now, we're going to come across the word sidereal several times in this section. Sidereal always means zooming out, imagining that you lived on a distant star and you were looking in at the Earth, Moon and Sun system from the outside. So whenever I use the word sidereal, it comes, I think, from Latin for star, then what I'm talking about is not standing on the Earth looking around. I'm talking about zooming right out the system, right out from the Earth, Moon and Sun, a long way away, looking in as though you were looking from a distant star. That's what sidereal always means. Would you see this? No, you wouldn't. You'd see the Earth spinning round. You wouldn't be bothered what people on the Earth saw. You would just see the Earth spinning round. And if I said to you, how long does it take the Earth to go round? You would time the time it took to do one spin. Okay? That's called a sidereal day, whereas that one is a solar day. You need to know both times, and very importantly, you need to know the 4-minute difference. Okay? Now, the big mystery, obviously, is why the two things should be different, and that's hopefully what the diagram on the screen shows you. Okay? Let's go over here. Now, if you have a look at the diagram, I think the sun's fallen off the top for some reason. Get the sun back. Sun's gone. There's the sun. Belt. Start down the bottom. Here's the Earth. All right. The Earth spins round, as we know, and the sun's over there. And a good way to think about it is if the Earth didn't go around the sun. Imagine the Earth didn't travel around the sun. Those two times would be the same. The time from sunrise to sunrise, or noon to noon, and the time for the Earth to spin would be exactly the same. All right. But what happens during the day is the Earth moves. All right. During this 23 hours, 56 minutes, or 24 hours, whatever you want, the Earth basically moves around. Okay. It moves around its orbit. Anyone like to estimate by how much?
1 degree.
It's about a degree, isn't it? 360 degrees in 365 days. Close to making no difference, it's about a degree. So the Earth doesn't stay in a fixed position, it moves around its orbit. Okay? So if this is your experiment, you've gone out, you've done your shortest shadow experiment, you said, right, there's noon, start the clock, and I'm going to wait, I'm going to do the shadow stick experiment all through the night, and I'm going to wait until I get my next noon. What will have happened? Yes, the Earth will have spun round. If that's the only bit you think about, then those two things ought to be the same. But in actual fact, what's happening is the Earth has moved around by about 1 degree. So imagine this is your shadow stick. Imagine point A here. Imagine you've got your stick in the ground. The sun here is directly overhead. I suppose you don't live in Skipton. So imagine point A is where you are. You've got your stick, and the sun is directly overhead. Okay. Now the Earth starts to turn, so you start to get carried round the Earth like that, and also round in the Earth's orbit. 360 degrees. Well, let's do that. Let's go from A all the way around like that. What are we actually going to do? We're going to go around to there. It's at the 12 o'clock position. Okay. So can you see on the diagram then, if you just waited 23 hours and 56 minutes, what would happen is you'd be back to that point there. You wouldn't be back to pointing at the sun. It would be just pointing vertical again. All right, I should label that point. Now, would the sun be overhead? If I was here,
No.
it wouldn't, would it? Where have I got to get the sun overhead again? You see, it's got to go round to there, which takes another 4 minutes. All right. So people on the Earth, what did they observe? They observed this. Yeah. Not 360 degrees, because 360 degrees won't get the sun back to the same place in the sky. Imagine this little person with the sun overhead, if they just do a 360, then now, because the Earth has moved around its orbit, the sun is no longer at its highest point. You've got to wait another 4 minutes to get the sun's gravity overhead. Okay? So hopefully this diagram shows you why there's a 4-minute difference. All right? The Earth takes about 4 minutes to turn through 1 more degree. All right? A nice way of thinking about it, the sidereal day is 360 degrees. But the synodic day, how many degrees does the Earth turn in a solar day? It's 361, isn't it? All right? In a solar day, the sun turns 361 degrees. Okay? Why 1? Because basically the sun has moved. Sorry, it appears that the sun has moved from the Earth by 1 degree because the Earth is moving around the sun. Okay? Good way to think about it, if the Earth didn't go around the sun, these two would be the same. If you were surprised to find these two things aren't the same, it's because you're just thinking of the Earth and the sun as fixed. You've got to factor in that the fact the Earth moves slightly compared to the sun. Okay? Make sure you know sidereal, solar, the times, 24 hours, 23 hours, 56 minutes you need to know, and the fact there's a 4-minute difference we're going to come back to. All right? And in fact, we can link it up to, because there's some nice questions they ask about this. Let's imagine you've done your experiment with your shadow stick, you got noon, and then you waited for the next noon, it was 24 hours. Let's suppose you did that with a star. Comes back to the word sidereal. Let's suppose you watched a very bright star tonight, rising, getting to its highest point. You know the name of that point? The star reaches its highest point, it's said to culmination. Yeah. It's crossing your north-south line, which is called your meridian. Yeah. So things rise, they set. Everybody knows those words. Things rise, they set. They reach their highest point due south. It's not just the sun that does that, everything does that. So stars at night, if you watch them, reach their highest point due south. They're said to have culminated, got to their highest point, and set again. Let's suppose that happens at 23:08. So you go out tonight, you find a particularly bright star, you watch it, and it reaches its highest point at 23:08, let's say. Okay? What time will it do that tomorrow? One of the offers is 23:04 or 23:12. Yeah? I'm sure everybody's got one of those 2 times. We'll decide which time you think it is. Why have we gone for a 4-minute difference? Yeah, it's the 4-minute difference, isn't there, between the sidereal and the solar day. Which of these days does the star work to? Yeah. Things like the sun work on the solar day of 24 hours. So if I asked you this question about the sun, the answer would be 24 hours. If I said I did a shadow stick experiment, I watched the sun to its highest point, I did the same thing again to next day, you would get 24 hours. It's not called the solar day for nothing. The sun follows the solar day. It repeats its position in the sky every 24 hours, by definition. However, things like stars don't do that. All right? Stars do not follow the solar day. And why should they? What time the sun rises has got nothing to do with what the stars do. All right? What determines what's got to happen for that star to culminate the following night? What's the Earth got to do? Well, how much? Yeah. How many degrees does the Earth need to do to get the sun back in the same place? 361, because of the movement around the orbit. But how much has the Earth got to do to get a star? Yeah? Does the star, pick your favourite star, does it move, as the Earth moves around its orbit by 1 degree, does that affect the direction of the star? Think of the scale of the God's eye view again. Here's the Earth going around the sun. Here's your nearest star, squillions and billions of light years away. There's a direction you look from the Earth to see your favourite star. What about next day when the Earth has spun round? Does that affect the direction the star's in? How much has the Earth moved in 1 day? It's moved around its orbit by 1 degree, hasn't it? Yeah? Moving around your orbit by 1 degree. If you're looking at the sun, does that affect the direction of the sun? Well, yes, it does. On my diagram, by quite a lot. But imagine we weren't looking at the sun. Imagine on this scale you were looking at a star 100 million light years away. The Earth doing this, is it going to have much effect on what direction you look to see the star? No. All right. The point about the sidereal day is you're considering things like stars, which are immense distances away. So the Earth whizzing around the sun and moving around its orbit by 1 degree has absolutely no effect whatsoever. So how many degrees, this is the key thing, how many degrees does the Earth, how many degrees does the Earth need to do to get a star back in the same place? The answer is 360. Here's the star, here's the Earth is doing that, it's just moved by 1 degree, it's the same direction, okay? So, how long will it take to go from one culmination to the next one? It's going to be 23 hours, 56 minutes, all right? So, do you need to go to 2308 again? How long is it between 2308 and 2308? 24 hours. You don't need 24 hours. Not for stars, because the Earth moving around its orbit 1 degree has no effect on the position of the stars. Even the closest star at 4.5 light years is massively too far away. For the 1 degree movement of the Earth every day has no effect. All right? So the correct answer is that one. All right? If they ask this as an exam question, a star culminates at 2308, at what time would an observer need to observe on the next day? The answer isn't 2308, it's 2304. If it was the sun, it would be 2308, although a rather strange question. But the sun would come back to the same position in the sky, 2308, but a star wouldn't. A star would go round 23 hours, 56 minutes. All right? So you'd only need to go to 2304. Okay? What about the next day?
24 hours.
That's it, it'd be 11 o'clock, wouldn't it? What about in 100 days' time? In 100 days, 3 months, roughly, what time would this be happening?
10, 20.
Well, it'd be 400 minutes, wouldn't it? 400 minutes off of that? What's 400 minutes? Is 6 hours and something, isn't it? Do you get the idea? Every day, the stars are kind of dropping back. The clock on the wall, or the clock on your wrist, and the stars drift by 4 degrees every day. So you do this at 2308 in October. If I say let's try it again in 3 months' time, what will happen is you go outside. This is trying to happen now 6 hours earlier. This is happening at 5 in the evening. So you go out at 2308 and look for the same stars. And in fact, if you look for that star at all, what will the problem be? It's culminating at 5 p.m.
The sun.
Yeah, you won't see it. A few days later, a few months later, it's drifted back into the daytime sky, isn't it? Do you understand now why you can only see Orion in the winter? Yeah? This could be one of the stars of Orion, and this could be November 2308. What time is it going to be culminating and come round to June? It's going to be culminating at 2 in the afternoon, which means you can't see it. So if you ever wonder why there are winter and summer constellations, it's because basically the sun, as we said right at the start of the course, the sun doesn't stay in the same position amongst the stars. It moves around. Another way of thinking about it is the solar day, which governs the sun, isn't quite the sun. I can't do this. It's like rubbing your head and patting your tum, isn't it? But the solar day and the star day are not going round at the same rate. They drift out of each other by 4 minutes a day. Can you imagine that? I can't do this, but like 2 circles going round, but one is going around 4 minutes slower than the other. And 2 points are just going to drift apart, aren't they? Okay? So this is important for sidereal and solar day, but also it affects the motion of the stars, all right? Things rising and setting, it's only the sun that does 24 hours. The stars and things do the same thing in 23 hours and 56 minutes. Okay?